One of the things that we're going to be interested in tracking for our systems is going to be the change in the Gibbs energy that's related to the vaporization of the components in a solution. So in other words, we're interested in a phase equilibrium that's going to exist, say, between two components in a liquid solution with their vapors in the gas phase. Now this is not dissimilar, if you will, to some of the expressions that we were writing earlier in Module 4, where we were, for example, writing down that the total Gibbs energy was equal to a component that was due to the liquid part and a component that was due to the vapor part. And so what we want to do is to generalize this to a two-component or more component system. So I am going to limit us now to two components, but now this total Gibbs energy is going to have a contribution from component 1 and a contribution from component 2. Furthermore, each of these components is going to exist both in the solution phase and in the vapor phase. So I'll have that the total Gibbs energy could be written as a component for component 1 in the solution phase plus component 1 in the vapor phase, and component 2 in the solution phase and component 2 in the vapor phase. Actually, I probably should have written the subscripts in the opposite order for these two. All right, that's a little bit better. All right, so what I want to do, though, is focus on one of these components, because it will turn out that these are always additive, and component 1 in the solution phase can only be converted to component 1 in the vapor phase. It cannot be converted to component 2 in the vapor phase. So I don't need to worry about sort of cross terms that are coming in here. So I'm going to focus on this part of this free energy, this part of this Gibbs energy change, and see where that leads us. Okay, so for component 1, what can I write? Well, I can write that component 1 has a change of Gibbs energy. So I'm going to now convert all these things to change. It'll be a change in the solution part plus a change in the vapor part. So something like this. And each of these now I can write correspondingly as a differential, a partial, keep writing S, I don't know why, a partial of G1 with respect to NS1 with all of the other n's constant, as well as T and P, times dNS1. Okay, this NS1 is the moles of 1 in solution. Similarly, I will have a term that looks like this for the vapor part, dG1, partial with respect to the number of moles in the vapor phase, with all of the other things held constant, as well as T and P, times the change in the number of moles for component 1 in the vapor phase. So dV1 will be the same for vapor. All right, so this way I can track how much stuff is in the solution phase here and in the vapor phase here. But notice that these two have to be related to one another. I can't convert component 1 into component 2 when it goes into the vapor phase. So in fact, I'm always going to have a relationship that says that the solution phase, the change in the number of moles of the solution phase is always the negative of the change in moles of the vapor phase. So I'm directly converting one into the other. I also want to note that these quantities that I have written here, these partial derivatives, are in fact just the chemical potential of component 1 in the solution phase and the chemical potential of component 1 in the vapor phase. All right, so these are things that should look very familiar to us. So now, if I want to write my total Gibbs energy change for component 1, and I substitute these things in, I'll have that it's simply the chemical potential in the vapor phase minus the chemical potential in the solution phase times the change in the number of moles in the vapor phase. Now, what I've done is I've used this relationship here to write everything in terms of the change in the number of moles in the vapor phase. Okay, since the solution phase is the negative of that, that's why I get the negative sign here. And so it's a difference between these two. Now, having written this, I can also draw some useful conclusions. For example, I know that dG1 for a spontaneous change has to be less than 0. So if this is the case, there are a couple of ways I can generate that. I can have the set of terms in the parentheses be less than 0, in which case I would have that the chemical potential of the vapor phase is less than the chemical potential in the solution phase, and that the change in the number of moles in the vapor phase is positive. All right, so this would correspond to evaporation, and it's telling us that things will evaporate spontaneously only if the chemical potential of the vapor phase is less than the chemical potential of the solution phase. Likewise, if the signs of these are, or I should say the magnitudes of these are opposite, if I have that the vapor phase has a greater chemical potential than the solution phase, then that means that this change in the number of moles of the vapor phase must be less than 0. In other words, I'm not evaporating anymore, I'm condensing. I'm moving moles from the vapor phase into the liquid phase, and that would cause this thing to be negative. All right. Now, this is great for determining spontaneity of these processes, but we also know that when we create a solution and it puts stuff in the vapor phase, that these things ultimately reach some equilibrium, so that we ultimately reach a point where the vapor and the solution are going to be in equilibrium with one another. All right, so at that point, we know that we must have the condition that the vapor phase chemical potential is equal to the solution phase chemical potential for component 1. The same would be true for component 2 and for any component that happens to be part of this solution. We always must have this when we have an equilibrium system. All right, but we can use this now to learn something very special about the vaporization of solutions in the following way. Let's write down a general equation for the chemical potential of our vapor for component 1. So, for example, our vapor for component 1 at some pressure P, and I'm going to assume that all of these things are going to happen as an isothermal process. So we're not changing the temperature. The only possibility is that the pressure could change. All right, and this is going to be equal to this this chemical potential of component 1 at some standard pressure, we'll say 1 bar, plus RT log of the pressure of this component over 1 bar. Okay, and if I'm in the solution, if I'm talking about the solution, because of this relationship, I know this must be equal to the chemical potential of the solution for component 1. All right, well, that's interesting. All right, so the condition of equilibrium always allows us to relate these to one another. So notice that we're relating the chemical potential of the solution to a reference state for the vapor, plus a term that depends on the pressure of that particular component. Now, remember that we're also going to have an equilibrium if we have that pure component. So let's say I have that pure component, and I want to measure its pressure in the vapor phase. Well, that pure component now would be written, if you will, and I should probably write this as a star because I've got the pure component, as the same reference point. Okay, so these are going to be the same because a vapor is a vapor, and at 1 bar, it's 1 bar. Okay, but now since I've got the pure chemical potential, now the pressure that I'm measuring for component 1 is the vapor pressure that I would have if above a pure liquid, above the pure liquid. So this is, I should probably write this out here, pure component 1 is this equation. So all I'm doing is I'm comparing the chemical potential for the vapor of component 1 to its pure liquid, and at equilibrium I'll have this relationship. Okay, so let's put a star there so that we're identifying this as the pure liquid. Okay, well, the interesting thing about this is that I can subtract these two from one another, and this term is the same in both of these equations. These terms can be combined in both of these equations, and I'm going to focus on these terms rather than these terms. I mean, these terms are interesting too, but these are the ones that I care about in this particular instance. So when I subtract these two equations from one another, what am I going to have? Well, on the left-hand side, these terms are going to cancel, and I'm going to end up with the following. I'm going to put this in a different color. I'm going to have RT of log P over 1 atmosphere. And remember, this is P1 of the solution minus RT log of P1 of the pure liquid. And both of these are respect to 1R. Now, whenever I subtract logs like this, this is just equal to RT log of P1 over P1 star. So what we're doing is we're actually comparing the vapor pressure of the component of a solution to its vapor pressure for the pure liquid. And this is going to be equal to mu of the solution minus mu of the pure liquid. So now we have a way of relating these things to one another. We could also have written this as mu of the solution at some pressure P, I should say P1, is related to mu of the pure liquid at pressure P1 star by this quantity. So this enables us, if you will, to connect the behavior of a component in a solution with its behavior as a pure component. And that's a really invaluable tool to have in our toolkit when we begin considering other thermodynamic properties of solutions.